Hello, people. Today we are going to learn about the crankshaft in a deep diven way. This is a part that turns the engine power into rotation. We look at the main journals, the crankpins, the webs, the crank radius, balance masses, oil weighs, flywheel, spigot bearing, timing, drive, and even the manufacturing processes that help the crankshaft survive millions of engine life cycles. And I'll keep the technicality and the terminology, but we'll explain it in plain English. So if you want to understand the complete crankshaft, this is a video for you. Let's know about what the crankshaft do. So what is the main job? So the crankshaft converts reciprocating motion of the pistons into rotational motion. So the pistons in the engine moves up and down, but the crankshaft rotates. Now, reciprocating sounds completely. It isn't. It is simply back and forth movement. In an engine, the piston moves up and down. The crankshaft turns that movement into location, and that is eventually used to drive the vehicle. Combustion into rotation. Um, think about power pad. Combustion process produces pressure. That pressure pushes the piston pushes the connecting rods transfer the force into the crankshaft. The crankshaft rotates, and the rotation is then submitted through the transmission and drive train to the wheels. So this is the process. Is combustion. The combustion pushes the piston pushes the connecting rod, the connecting rods forces the crankshaft to rotate. That rotation is the same rotation that is happening in the transmission all the way to the wheels. Okay, but there is where things here is where things become interesting. The crankshaft isn't just receiving power from the piston. On a multi-cylinder engine, several cylinders are producing power at different points in the engine life cycle. The crankshaft takes all those individual power pulses and combines them into one rotational force. And it is doing this while rotating at very high speeds. The crankshaft has to be incredibly strong, but it also has to be accurately manufactured and properly balanced. So look at the case and the shape of this crankshaft. If you ever have seen a crankshaft outside an engine, you may have noticed something. It does not look like a normal slate shaft. It is full. It is full of offsets, journals, and large sections of metal, and every one of those features has a job. Let's start with the main journal. A journal is simply a part of a shaft that rotates inside the bearing or inside a bearing. So main journals are the parts of the crankshaft that rotates engine inside the engine's main bearing. They sit along the main center line of the crankshaft. Now, next to those, we have the crankpins. The crankpins is where the connecting rod is attached. And but here is something important. The crankpin is offset from the main journal. It isn't sitting on the same center line, and the offset is called the crank radius. Now, ask yourself why the offset matters and why is that offset necessary. Now, here's something to think about. Imagine the crank pin. We are sitting directly on the center of the crankshaft. Would the connecting rod be able to make the crankshaft rotate as the piston moves? The answer is no. You need that offset. The piston moves up and down, the connecting rod moves with it, but the crank pin is offset from the crankshaft center line. The force from the connecting rod produces rotation. That is basic mechanical principle behind the crankshaft. Now let's learn about the webs and the fillets. How are the crank pins connected to the main journals? Through the webs are the large sections of the crankshaft that connects the main journals to the crank pin. And there is another feature that you should pay attention to. Where the journals meet the web, you won't normally find a sharp corner. Instead, there are curved transitions. That is a fillet or radius. Why not make it a sharp corner? Because sharp corners create areas where stress can concentrate. But remember what the crankshaft is dealing with. Every combustion event is applying force to it. Even the crankshaft, it's when the crankshaft will rotate. Then another cylinder fires, another force is applied, and another for thousands and thousands of engine cycles. So that small curved fillet is actually extremely important to the strength and durability of the crankshaft. There's also the balance masses and counterweight. And here is a question: why does the engine shakes itself apart? Well, one major reason is balancing. Some crankshafts web extended to form balance masses. These masses help balance the rotating component of the engine. Remember, the crankshaft is rotating alone. It's connected to connecting rods and pistons. Those components create forces that need to be controlled. If the rotating assembly wasn't properly balanced, the engine would produce excessive vibration and you would definitely feel it. But here's something interesting: some engines can never be perfectly balanced. Take single cylinder engines. It is impossible to completely balance all of its rotating and reciprocating forces. At high engine speeds, centrifugal force acting on the clamp pins can place heavy loads on the nearby main bearings. So engineers can extend the crankshaft webs to create a counterbalance mass. This produces a counter centrifugal force that works opposite direction, or that works in the opposite direction. This will result in reduced loading on the bearings. What does throw means? Now let's talk about the word you may hear when studying crankshafts, the crank throw. So, and this word can be confusing sometimes. Throw is used to mean the crank radius, but older terminology can define it differently. In that case, the throw is the diameter of the circle traveled by the crank pin, and the diameter is equal to the piston stroke. So crank circle diameter is equal to the piston stroke. Because the word can mean different things, it's better to use more specific terms. If you are walking about the distance from the center of main journal to the center of the crank pin, call it the crank radius. You are walking through the full diameter of the crank pin's circular path, call it the crank circle diameter. Throw can also refer to the crank pin diameter with its adjacent webs and main journals. So when you are reading a technical manual and you see the word throw, don't assume it has only one meaning. Next, let's speak of a multi-cylinder crankshaft support. Now, here's something you might not have thought about. Does every crank pin have a main journal on both sides? Not always. For example, a throw crankshaft has only two main journals. The crank pin can be connected by what's called a flying web. However, inside However, on most modern engines, the crankpin will normally have main journals on each side. This provides strong support for the crankshaft. A common example is a four-cylinder engine with five main bearing journals. So, when you hear someone say five main bearings, they are talking about the points where the crankshaft is supported by main bearings. And by the way, if you've reached here, kindly subscribe, kindly comment, kindly share. Yeah, this is not for everyone, I know. So kindly help reach other technicians. Now let's go to the flywheel. At the layer of the crankshaft, we normally find the flywheel, and this is where the crankshaft's rotational power begins its journey towards the transmission. The flywheel is attached securely to the rear of the crankshaft, but there's an important detail. The flywheel is supposed to be installed randomly. It should normally fit one specific position. Why? Because the crankshaft and the flywheel are balanced. They are balanced separately, but they are also balanced in an assembly. If you change the relationship between them, you can create imbalance, and the imbalance means vibration. Imagine the crankshaft has a small amount of imbalance. The flywheel also has a small amount. Both may within acceptable limits individually, but if they are installed so that the two imbalances add together, the vibration become more severe. In some cases, turning the flywheel 180 degrees can change that relationship. Correct flywheel positioning matters. Flywheel top dead center reference. The flywheel can also reference or have a reference point that represents top dead center. Top dead center, TDC, that's the meaning. That is a position where the piston reaches the top of its stroke. The reference point can be detected by a sensor, and this information can be used by the engine management system. The system needs to know exactly where the crankshaft is positioned. That information can be used for controlling engine operations. If you are looking at a flywheel and thinking it's just a heavy metallic disc, think again. Its position can be important for both balance and the engine position information. And now, how is the flywheel secured? At the rear of the crankshaft is a fringe. The fringe fits into a counter bow hole in the center of the flywheel. Then several bolts secure the flywheel into the crankshaft. The bolts pass through the holes in the flywheel. The screw into the threaded holes in the crankshaft fringe. There are also individual dowels. Dowels help to take sharing loads, and dowels or bolts can be arranged unevenly so that the flywheel can also be installed in the correct position. A locking arrangement is used to prevent the fasteners from losing. So if you have ever wondered why manufacturers don't simply put equally spaced holes around the flywheel, now you know. The correct positioning matters. Now let's speak of the crankshaft railways. This is one of the most important parts of understanding the crankshaft. The crankshaft is rotating at high speeds, and the crankshaft journals are operating against bearing under very high loads, so they need lubrication. The engine oil pumps send oil under pressure to the main bearings inside the bearings is is inside the bearing is an oil groove. The pressurized oil enters this groove, but now becomes the clever part. How does the oil reach the crank pin? The crankshaft has internal oilways. These are passages drilled through the crankshaft. The passages start at the main journal, travel through the web, and comes out at the crank pin. So the oil travels, that is from the oil pump to the main bearing to the crankshaft always, then to the crank pin. This allows the crank pin bearing to receive lubrication, and remember the crankshaft is rotating, so the oil supply has to work while everything is moving. And that is why the position of the drilled passages is carefully designed. Now, where does the oil go? That is another important question. Now, we have another problem. Oil is being supplied to the rear main bearing. The crankshaft extends through the rear of the crankcase, so some oil is naturally trying to escape around the shaft. Obviously, we do not want that. And there is another reason. If the engine oil escapes and reaches the clutch plate, it can contaminate the friction surface, and that is bad news for the clutch operation. So the engine needs a way of keeping the oil inside. One common solution is a lip type oil seal. It's made from synthetic lumber and supported by a steel shell. The sealing lip places lightly against the rotating crankshaft, and a small gutter spring helps maintain that contact. The shaft can rotate while the seal prevents oil from escaping. Next, we have fingering and scroll seal. These are other methods too. One is a fingering. It's basically a thin ring or fin found around the crankshaft. As the crankshaft rotates, centrifugal forces draw oil away from the shaft. The oil is collected in a cavity and drain hole allowed it to return to the crankshaft or to the crankcase. Sorry, rather. Another method is scroll. A helical groove is machined into the crankshaft surface. This think of this like a coarse screw thread. As the crankshaft rotates, the groove helps move the oil back towards inside the engine. So instead of allowing oil to escape, the design helps return into the crankcase, and some engines use more than one of those oil control methods. The spigot bearing. And now let's connect the crankshaft to the gearbox. The engine produces power, the crankshaft rotates, and eventually the power needs to reach the transmission. And the connection is through the clutch. The gearbox has an input shaft. The shaft is supported inside the gearbox, but what about the its front end? It also helps. It also needs support. So that is why the spigot bearing comes in. The spigot bearing is fitted into the layer of the crankshaft. The front end of the gearbox input shaft sits inside it. Depending on the design, the spigot bearing can be a roller type bearing, or it can be simply a bronze bush. So if the rear of the crankshaft is two important jobs, it's connected to the flywheel. It can support the gearbox input shaft. That's another reason this part of the crankshaft is so important. Nose of the crankshaft and timing drive. At the front of the engine is the nose of the crankshaft, and this end drives several components. One of the most important is the camshaft. The camshaft controls the opening and closing of the inlet and exhaust valves. In most engines, the camshaft is driven from the front of the crankshaft. The crankshaft extends beyond the front main journal, and that extension may be constant in diameter or stepped. Mounted on this area is the timing drive. Depending on the engine, it could be a timing gear, a timing sprocket for a chain, or a timing pulley for a belt. The crankshaft drives the timing chain or belt, which drives the camshaft. And this is where timing becomes extremely important. The crankshaft controls the piston position. The camshaft controls the valve position. Those two have the main has to remain synchronized. If they don't, the engine cannot operate correctly. Accessory drive and woodlaff key. And the crankshaft doesn't stop with timing system. Addition, Additionally, pulleys can be attached to the front. This can drive other belts, and those belts may drive the water pump, the alternator, the cooling fan, or depending on the engine, the power steering pump. So, one rotating shaft can be responsible for driving a whole collection of engine systems. But how do those pulleys stay correctly positioned? One common method is a woodlaff key. There is a lot in the crankshaft nose. This There's another slot on the pulley or sprocket. The key fits between them. It locates the components and transfers the drive from the crankshaft. Then a nut or the screw secures the pulley or sprocket to the end of the crankshaft. So the woodlaff key isn't simply there to stop something from falling off. It ensures the components rotate correctly with the crankshaft. Now we have the chain, belt, or gears. A timing chain. When the timing sprocket is enclosed inside the timing case, the accessory pulley are outside the timing cover. Because the timing chain operates inside the engine, the cover has to prevent oil from escaping. Some engines use gear train instead. The crankshaft timing gear becomes the first gear in the train. The gear then transfers the crankshaft rotation to the camshaft, and then there is a timing belt. Unlike the chain system, the timing pulley is normally outside the oil-tight timing case. The belt is protected by a cover. The front of the crankshaft also requires an oil seal, and just like with other lip type seals, the sealing lip should be lubricated before the pulley is installed.